In this episode, we're going to take something that sounds simple at first, keys, and treat it the way security people actually have to treat it, like fragile, powerful objects that can either protect your entire system or quietly unravel it. When beginners hear the word key, they often think of a password, or they picture a physical key that opens a door, and that intuition is helpful but incomplete. A cryptographic key is more like a permission slip that a machine can read, and it can grant very specific powers, like decrypting data, signing something to prove it is authentic, or letting one system talk to another without a human typing anything. In an AI security context, keys show up everywhere, protecting stored data, securing connections between services, and controlling access to model endpoints and related resources. If you understand how to rotate keys, store them properly, and separate duties so no single person can accidentally or intentionally misuse them, you've learned a core safety skill that keeps small mistakes from becoming huge incidents. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A good starting point is to clearly separate three ideas that people mash together: passwords, tokens, and cryptographic keys. A password is something a human remembers, which means it is usually short enough to type, and therefore vulnerable in ways that long random values are not. A token is often a temporary credential issued after you authenticate, and it can represent your identity for a limited time, like a wristband at an event that proves you already paid. A cryptographic key is typically a long random value meant for machines, and it is the secret ingredient that makes encryption and signatures work. In plain terms, encryption turns readable data into unreadable data, and the key is what makes the transformation reversible for the right party. Digital signatures let you prove something came from you and wasn't modified, and keys are involved there too, usually as a pair where one key signs and the other verifies. Beginners often assume the encryption algorithm is the secret, but modern security assumes the algorithm can be public, and the key is what must stay protected, because the key is the thing that attackers want. Once you accept that keys are high-value secrets, you can see why key management is not a nice-to-have. It is the lock on the lockbox. Key management is the full set of practices for creating keys, using them, limiting where they can go, tracking who can touch them, replacing them safely, and destroying them when they are no longer needed. In real environments, keys multiply quickly because different data sets, different environments, and different services each need their own secrets. That growth creates risk because humans are tempted to simplify, reuse, or stash secrets in places that are convenient. Convenience is where many breaches begin, not because people are careless, but because they are under pressure and they want things to work. Key management turns that chaos into a system with guardrails. Every key has a purpose. Every key has an owner. Every key has a safe home. And every key has a plan for what happens when it must change. This is especially important with AI systems because they often connect to many other systems, and each connection is a chance for a secret to leak. Storage is the first major pillar, because a key is only secret if it stays secret. Beginners sometimes store keys in plain text files, paste them into notes, or embed them directly into application code, which feels harmless until you realize how many places code and files travel. Code gets copied, pushed to shared repositories, sent to contractors, reviewed by others, and backed up across multiple systems. A key inside code is like leaving a spare house key taped under the doormat, except now the doormat is copied into 10 places and logged forever. A safer concept is to keep keys in a dedicated secret storage system where access is controlled, audited, and limited to what is needed. Even without naming specific products, the idea is consistent. Secrets should live in a hardened vault-like service, and applications should request them at runtime in a controlled way. This reduces the number of accidental exposures and makes it easier to rotate keys without rewriting and redeploying everything. Another part of safe storage is thinking about keys in 3 different states: at rest, in transit, and in use. At rest means sitting on disk somewhere, which could be a database, a configuration store, or a backup archive. In transit means moving across a network connection between systems. In use means present in memory while an application is actively using it to encrypt, decrypt, sign, or authenticate. A beginner might focus only on network encryption and assume that covers everything. But the most painful leaks often come from keys at rest, like a copied configuration file, or keys in use, like secrets lingering in logs or being captured from memory during a compromise. Protecting keys at rest involves encryption and strict access control, but it also involves reducing copies and ensuring backups do not become a secret graveyard. Protecting keys in transit means using secure channels and authenticating endpoints so you are not handing secrets to an imposter. Protecting keys in use means minimizing how long they live in memory, limiting which processes can access them, and avoiding debugging practices that accidentally print them. Rotation is the second major pillar, and it is one of the most misunderstood. Many people hear rotation and think it is a ritual you do because a policy says so, like changing a smoke detector battery on a schedule. The real purpose of rotation is to reduce the time window during which a stolen key is useful and to limit blast radius when you suspect compromise. If a key never changes, then any exposure becomes permanent access until you notice and fix it, which might be weeks or months. If keys rotate regularly, then an attacker who steals a key has a shorter window before it becomes useless, assuming your systems actually stop accepting the old key. Rotation also forces your organization to practice the process of changing secrets safely, which is valuable because emergencies are not the time to learn. The goal is not simply to rotate often, but to rotate reliably, without breaking systems, and with a clear method for phasing out old keys. It helps to separate planned rotation from emergency rotation because they feel similar but happen under different stress. Planned rotation is routine replacement on a schedule, done calmly, with steps that have been tested and automated as much as possible. Emergency rotation happens when you suspect a key is exposed and you need to cut off access fast, while also figuring out what happened. Planned rotation teaches you whether your architecture supports change, because if switching a key causes outages, people will avoid rotation and drift back into unsafe habits. Emergency rotation tests whether you can respond decisively under pressure without making things worse. In both cases, you need a concept called overlapping validity, where systems can temporarily accept both the old and new key during a transition period. That overlap prevents downtime, but it must be time-limited so the old key eventually stops working and the window closes. Rotation also depends on how keys are used, because not all keys can or should rotate the same way. Some keys are used to encrypt stored data, and changing them can be tricky because the old key might be needed to decrypt existing data. In those cases, a common approach is key wrapping, where a main encryption key protects smaller data keys, and you rotate the main key while rewrapping the data keys without re-encrypting all the data. Other keys are used for signing, where you may need to keep old verification keys around, so previously signed items can still be validated. That is a subtle point. Rotation does not always mean you delete the old key immediately. It means you stop using it for new operations and keep it only as long as needed for verification or recovery. If you delete a key too soon, you might lose access to data or break trust chains, which turns a security improvement into an availability disaster. So good rotation includes understanding the purpose of the key and the lifecycle needs of the system. Now we get to separation of duties, which is the third pillar, and it is less about math and more about human risk. Separation of duties is the idea that no single person should have end-to-end power over a critical operation, especially one that could be abused or could cause major damage by mistake. In key management, this might mean the person who can create a key should not be the only person who can activate it, and the person who deploys code should not be able to read production secrets. It can also mean that access to the secret storage system is separate from access to the systems that use the secrets, so someone cannot both extract a key and immediately use it to decrypt sensitive data. This principle reduces insider risk, but it also reduces accidental risk, because a second set of eyes catches mistakes. Beginners sometimes hear this and think it is only for large organizations, but the idea scales down. Even small teams can use role separation and approvals to ensure that high-impact actions require more than one person's decision. To make separation of duties concrete, Imagine a situation where an AI application uses a key to decrypt customer data before sending a small portion of it to a model for summarization. If a single developer can access the vault, retrieve the key, read the decrypted data, and also change the logging settings, that developer holds a lot of power. Even if they are trustworthy, this setup makes it easy for a compromised account to do enormous harm. A better design is to restrict direct secret access so applications can fetch what they need, but humans cannot casually pull production keys. Then you add controls so changes to secret access policies require approvals, and you log those changes in a tamper-resistant way. That way, if something goes wrong, you have both prevention and investigation support. The point is not to treat every person as a villain. It is to recognize that accounts get phished, laptops get compromised, and mistakes happen, and we want the system to be resilient to those realities. A related concept is least privilege, which means each identity gets only the minimum access needed to do its job. When applied to keys, least privilege means that a service should only be able to use the specific keys it needs and only for the operations it needs. For example, a service that only encrypts outbound messages should not also have permission to decrypt stored databases, and it should not be able to list all secrets in the vault. Another subtle point is that reading a key is often more powerful than using a key. A system can be designed so an application can ask the vault to decrypt something without ever receiving the raw key value, which prevents the key from being copied elsewhere. Beginners sometimes think access is binary. Either you have the key or you don't, but good key management introduces fine-grained permissions. Who can use a key for encryption, who can use it for decryption, who can rotate it, and who can disable it. That granularity is what turns keys from a fragile single point of failure into a controlled asset. Key management also has a monitoring and auditing side, because secrets are not just stored, they are used, and usage patterns can reveal trouble. If a key that normally decrypts a few records per hour suddenly starts decrypting thousands per minute, that could indicate abuse or automation gone wrong. If a key is being requested from new locations or at unusual times, that could be a sign of compromise. This is where beginners should learn to think like defenders, not only how to lock a door, but also how to notice when the door is being tested. Usage logs should capture enough information to investigate without leaking secrets, which means logging metadata, not the secret values themselves. You want to know which identity used a key, what operation was performed, and from where, but you never want the key to appear in the logs. When key access is treated like a critical event, it becomes much easier to detect misconfigurations and attacks before they become full incidents. In the context of AI systems, key management has a few extra wrinkles because AI workflows often involve data movement across boundaries. You might have a data store, a retrieval system, a model endpoint, and a monitoring pipeline, each with its own keys or credentials. That complexity can push teams towards shortcuts like sharing one secret across multiple components, which is a classic way to expand blast radius. A beginner-friendly rule is simple: avoid shared secrets across different purposes, because it makes it impossible to confidently say what was affected when something leaks. If one key is used for both staging and production, then a leak in a low-risk environment becomes a high-risk incident. If one key is used for both reading data and calling a model, then compromise of a single component can unlock multiple systems. Segmenting keys by environment, by system, and by purpose is the quiet discipline that prevents one crack from becoming a collapse. Another beginner misconception is that rotating keys solves everything, so storage and separation of duties are less important. Rotation is powerful, but it cannot fix the problem of keys being scattered everywhere. If a key is embedded in code, rotating it means you now have to update all copies of the code and ensure no old versions are still deployed somewhere, which is hard and error-prone. If many people have direct access to retrieve keys, then rotation does not reduce insider risk. It just changes which key they can retrieve today. If the process of rotation is manual and fragile, people will delay it, skip it, or do it inconsistently. In other words, rotation works best when storage is centralized and controlled, and when separation of duties prevents casual access. The three pillars support each other. Safe storage makes rotation easier. Rotation makes leaks less catastrophic, and separation of duties reduces the chance of misuse or accidental exposure. It is also important to talk about the life cycle of a key from birth to death, because beginners often only think about creation and use. Key creation should involve strong randomness and clear labeling so you know what the key is for and where it is allowed to be used. Key activation should be deliberate, because sometimes you want to create a key and not immediately start using it until systems are ready. Key distribution, if it must happen at all, should be minimal and controlled, because every copy is a risk. Key revocation is the ability to disable a key quickly, which is crucial during an incident. Key destruction is not just deleting a file. It is ensuring the key is no longer accessible anywhere, including backups and archive configurations. When you think in life cycles, you start asking better questions, like what happens if this key leaks? How fast can we replace it? And how do we prove we replaced it everywhere it matters? As you pull these ideas together, notice that good key management is less about fancy tricks and more about disciplined habits that reduce surprises. Rotation is about time and recovery, limiting how long a secret can hurt you and ensuring you can change it safely. Storage is about containment, keeping secrets out of places where they can spread and ensuring they are protected in every state. Separation of duties is about human safety, ensuring that high-impact actions require more than one capability and that compromise of one account does not equal total compromise of the system. When these are done well, they create a calm, predictable security posture where secrets are managed intentionally rather than by accident. When they are done poorly, you see the opposite: mysterious outages during secret changes, leaked credentials in places nobody thought to check, and incidents where investigators cannot even tell which keys were exposed. To close, key management is one of those topics that can feel like background noise until the day it becomes the only thing that matters, because a single leaked or misused key can instantly bypass other defenses. Beginners do not need to memorize cryptographic algorithms to do this well, but they do need to internalize that keys are powerful, fragile assets that must be handled with care. Rotating keys on a reliable schedule and having a practiced emergency rotation process keeps the damage window small when something goes wrong. Storing keys in a controlled vault-like place, rather than scattering them across files and code, reduces accidental exposure and makes change manageable. Separating duties so no one person or single compromised account can create, extract, and use secrets without oversight reduces both insider and external risk. If you carry those three pillars forward, rotation, storage, and separation of duties, you will have a practical foundation for securing AI systems in a way that holds up when the real world gets messy.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.